Hello, this is Mr. Smith with the first reading quiz of the BC year. This reading quiz will be about the average value of a function, and we're going to connect this to the idea of average, which you've already seen in previous classes, the idea of summing up numbers and dividing by the total number of numbers. And the question that we're going to ask ourselves is, can we apply this same principle to a function? Can we find the average value of a function? As you might expect, since the end of AB calculus was all about integration, we're going to connect this idea to finding the integral of a function. So let's take a look at the formula. The graph below shows the graph of y is equal to x squared on the interval 0 to 3, with the black bars representing the height of the function at certain x values. So how are we going to find the average value of a function from a to b? Well, essentially the idea is that we're going to add up all the function values and divide them by the length of the interval. Now, if you remember, typically we find an average by summing the numbers and dividing by the total number of numbers. Well, that's a little bit tricky since there's an infinite number of function values even on a finite interval. So how do we get around that? Well, let's introduce some sigma notation. The idea of an average involves adding up numbers. So in the very first part of this inequality that you see on the screen there, we're going to add up the first n function values and divide by n total function values. That's just the idea of summing up our function values. I put a little trick with the second part of the inequality and multiply and divide by b minus a on the top and the bottom of our fraction. The reason why I did that is so that I can rewrite our sigma notation as the sum from k is equal to 1 to n of f of x sub k times b minus a over n, leaving that second b minus a on the bottom. Well, you may recognize that first numerator part. That looks a lot like a Riemann sum, where we've got the function value representing the height of a particular rectangle and the b minus a over n representing the width of the rectangle. Well, if it's a Riemann sum, then we can rewrite this as an integral, especially as the limit as n goes to infinity. We get the integral from a to b of f of x dx over b minus a, and this will be our formula that we use for finding the average value of a function. So let's take a look at an example that applies this formula. What is the average value of f of x is equal to 4 minus x squared on the interval 0 to 3, and then at what value of x does the function reach its average value? For the first question, all we need to do is apply our formula. The average value of f of x would be the integral from 0 to 3 of 4 minus x squared dx over 3 minus 0. It's important to remember the divide by 3 minus 0. That's similar to dividing by the number of numbers, and it's actually the part that people miss the most. They tend to find the integral but forget to divide by the length of the interval, which is certainly important. We're going to be dealing a lot with finding antiderivatives in this particular unit, so we'll need to be familiar with all kinds of different techniques for finding antiderivatives. In our case, our antiderivative is pretty easy to work with. It's 4x minus x cubed over 3, which we'll evaluate from 0 to 3. We plug in and evaluate using our FTC. Get 12 minus 9 over 3, which is 1. So what does this mean? This means that if we were to take all of the function values from 0 to 3, which is an infinite number, and average them, we would get an average function value of 1. Kind of the idea of trying to balance the function. The second part of the question asks us, at what value of x does the function reach its average value? Well, if we want to find where the function reaches its average value, we set the function equal to our average value, which in this case would mean that 4 minus x squared is equal to 1. When we solve, we find that the function reaches its average value when x is equal to 3. But Mr. Smith, you'll say that you can have a possible answer of x is equal to negative root 3. Well, we only want the answer that's actually on our interval. In this case, the interval is 0 to 3. So we only use the positive square root here. A second example. If an object has velocity v of t is equal to 2t cubed minus 3t squared meters per second on the time interval 1 to 3, what is the average velocity of the object from 1 to 3? And a second question, what is the average acceleration? Average velocity is asking us to find the average value of the velocity function. So we apply our formula, the integral from 1 to 3 of 2t cubed minus 3t squared dt over 3 minus 1. Pretty easy antiderivative to work with. We get 1/2 t to the fourth minus t cubed, evaluated from 1 to 3, again divided by 3 minus 1. We plug in our values, as you can see on the screen, and reduce it down to 7 meters per second. So what that means is on the time interval 1 to 3, our average velocity value is 7 meters per second. The second question asks us for average acceleration, which is a different question, but very similar. We're going to apply our average value function to a of t dt. When we do that, we get the integral from 1 to 3 of a of t dt divided by 3 minus 1. We could go through and find our acceleration function and then integrate it again, or we could realize that when we integrate acceleration, we get velocity. And so we can apply our FTC to the velocity function. We get v of 3 minus v of 1 over 3 minus 1. When we plug in 1 and 3 into our velocity function and evaluate, we get 14 meters per second squared. Remember the appropriate units. So you may have noticed that average acceleration is just average rate of change for velocity. And in general, the average value for a derivative is the average rate of change for that derivative's antiderivative, as acceleration and velocity are. So average value and average rate of change are certainly related to each other, but not the same. One theorem that relates to average value is what we call the mean value theorem for integrals. And what it states is if a function f is continuous on a closed interval a to b, then at some point c in a to b, f of c is equal to the integral from a to b of f of x dx over b minus a. In English, what that means is the continuous function equals its average value for at least one spot on the interval. So why do we call this the MVT for integrals? Notice that the average rate of change of capital F is the integral from a to b of f of x dx over b minus a, as I just mentioned. So what this means is we are applying the MVT to the capital function f of x, or the antiderivative, hence the mean value theorem for integrals. As you can see on the screen there, the integral from a to b of f of x dx over b minus a is the average rate of change for capital F, which will then be equal to little f at some point c. Hey, that looks like the MVT, except for capital F. One way of rearranging it, which will be helpful for the next slide, is to realize that the integral from a to b of f of x dx is equal to f of c times b minus a. Let's take a look at what that means geometrically. So, a graphical representation. We just said that f of c times b minus a is equal to the integral from a to b of f of x dx. Well, one way that we can represent the left side of that inequality is as a rectangle, where f of c is our height, denoted by the height of 3 on our diagram, and b minus a is the length of the interval, or the width of the rectangle. So what this mean value theorem says is that that rectangle area is equal to our signed area, where the height of the rectangle is whatever the average value of the function is. It's a pretty powerful theorem. Looking at it graphically, what I'm saying is that the area 1 plus the area 3, which is the area of the rectangle, has to equal the area of 2 plus the area of 3, which would be the signed area underneath the function. As you can see, the area of 1 and 2 look pretty similar and in fact do equal to each other. And the area of 3 is a shared area between the rectangle and the function. So those two areas balance out, 1 and 2.